Thank you, Chairman. Once again, I am before you. Thanks to Manoj. Thanks to colleagues here in Bikaner. Well, I'm out of this research work for last so many years, mostly doing administration. So might be this is work which we did over last 30 years plus, along with my colleague scientists in DRDO, and most of those scientists also did PhD with me. So it is their work I am presenting, and nothing much of mine in this one. But very important thing which I want to highlight here, the title is Magnificent World of Materials. Really, materials has got magnificent world. Right now, Michel has talked about, again, materials, to neuroscience, neurology, human-brain interaction, all those kinds of things. So you think of the area, and materials are very important. And another thing is, Dr. Yakhmi sir has mentioned, something very interesting is, when you do the research, focus is very important, observations are very important. You have to think about and how things can emerge if you are really having keen observations. And most of the results which I am going to present are observations only. Many of the things are purely observations, many of the things are innovations. Another point which we kept in mind while working, being in DRDO, most of our work had to be applied in nature. When you say applied in nature means they have to be simple methods of making it. They should be scalable. You should be able to make in large quantity. Like some of the materials we were making in kilogram. When I say nano composite, we started making in kilograms. Conducting polymers we started making in kilograms. Ferrites we started making in kilograms. Because if you don't make in those quantities, they cannot be used for real life applications. And more so when you scale up, how do you manage the properties and how do you manage the consistency of the properties, reproducibility of the things. But I'm not going to talk about those things, but these are things which are very important when you want to do the applied research. Currently I'm at IIT Jodhpur. First work I am talking about in nano composite of metal oxides. This somewhere we started in 93. We were having very meager facility, and perhaps one of the facility was Mosbar, and that was my PhD topic. So we thought that we should start working with materials containing iron. And we started thinking, and we developed some material. And when we studied its Mosbar pattern, it's not there, but then it showed relaxed spectrum, which indicated that this can be a small size particle, and that time the term was being used as ultra fine particles. And I had lots of paper studied on ultra fine particles. Some Swedish group was there, and then but we didn't have any facility. So I went to SSPL Delhi. One Dr. B.B. Sharma used to be there. I took that material and we took XRD spectrum, and then broad lines were there. So I was not really aware of XRD also that time. But Dr. Sharma mentioned that broad lines indicate small size particles. And based on that line width, we calculated particle size to be 50 nanometer. So that was an accidental discovery of making nanoparticles, nano composite material. And this material we made in kilograms. So 5 kg base scale we made this material. Another work was one of my colleague. He wanted to do PhD. So he said that I want to do PhD from IISc Bangalore. We had interaction with one Professor T.R.N. Kutty. He was there in IISc Bangalore. And he said that I want to do PhD from IISc Bangalore. We were in Jodhpur. I said, why don't you do your PhD from Jodhpur? How does it matter? But he thought that IISc Bangalore has got much better facilities and better scope of doing. I said, what you do, if you leave, because he was in job, if you leave the job and go to IISc, then when you come back, you will be out of place. So better to remain in job, do your PhD, do from here and collaborate with IISc Bangalore. And it was beautiful work he has done. And he is currently, head of cancer nanotechnology at Amrita Institute of Medical Sciences in Kochi. He has got about 30 patents, 2 startups, a few PhD students and all those things. This was a wonderful work. This is first time we showed that through simple chemical method, you can make nanophosphor materials of zinc sulfide. If you see TM spectrum, it shows particle size, very uniform particle size, which is of the order of 2 to 5 or 2 to 3 nanometers. And if you see XRD pattern, it gives broad peak, which is clear indication that these are nanoparticles, but with very simple chemistry and at room temperature. This was the synthesis which was done. And yeah. Slow. Yeah. This is something very interesting. You see, we tried doping. One is manganese, another is aluminium. Now, what happens when you decrease the quantity of or increase the quantity of manganese and reduce the quantity of aluminium? If you see the color change, it is coming from, say, green to orange. So what happens? Now you can tune any color between green to orange by just wearing the doping. Suppose you increase the manganese, you will go to the orange side. You decrease the manganese and increase the aluminium, you will go to green side. And what you can do, you can control put at any point. There is nothing you can have. These are 4 figures which are shown, 4 colors, but you can achieve any color. So again, it has been shown that through very, very simple method. It is again very simple chemistry, room temperature method, and very simple method. You can tune color from green to orange, and you can have any wavelength you want. Say any wavelength you want, you can have. Similarly, we could develop self-assembly, and we could show that you can have nano rod kind of thing. So this is another work on zinc sulfide. Then this is very interesting work. This is core shell. You see, core shell means what happens? You have got zinc sulfide material. When there is a vacancies, it will give blue color. As you heat it, a layer of a shell of zinc oxide is created. As you heat it, the thickness of the layer increases. So if you see here, if you start with blue color, and as you increase the temperature, you get to the red color. So again here, by varying the temperature. So earlier what we did? By varying the concentration. Now what we did here? By varying the temperature. So by varying the concentration, you can tune the color. By varying the temperature, you can tune the color. And it's very interesting that there is a core of zinc sulfide and shell of zinc oxide. And as you increase the thickness of zinc oxide, this color changes and you can tune the color. So how beautifully you can tune the color through very simple processes. This is another example, rare earth nanophosphor material. This we said multifunctional material, again core shell material. Now shell is luminescent material, core is magnetic material. So you have got magnetic material as a core and luminescent material as a core shell. So you can have a multifunctional property wherein you can have luminescence also and you can have magnetism also. And it has got a lot of applications. Now another class of material. I am trying to put across that there is a range of materials you can make very simple process. This is zinc oxide materials. This is single step process, and you can see that you can beautiful geometries of these materials, and also you have got magnetic and luminescent properties here again. Here you have you can see tuning of particle size. We call it quantum dots. So you have got say 4 nanometer, 6 nanometer, 8 nanometer particles, and you are showing that how with particle size color can be varied. So now it is third kind of tuning. Now this tuning is particle size based tuning. So now a different kind of tuning you are doing. So that's why I said it is a magnificent world of materials, because you can do many kinds of things in these materials. Okay. This is another example of silver nanoparticles. Now here again, shape and size play a very important role, and these are basically plasmonic particles. Because of plasmonic frequency, they give different colors. And you can see we could get range of colors by varying either size of the particles or by varying shape of the particles. So now here third aspect, another aspect comes that you vary the size, you get the change in color, you vary the shape, you change in the color. So now it is shape, design, color. So shape designing is there. So you can design materials in a beautiful way. This is silver nanoparticles showing, luminescence, and you can see how uniformly these particles are of the order of around 3 nanometer or something like that. Again, I am emphasizing here that all these materials have been made through very simple chemical processes, most of them at room temperature, some of them at higher temperature, but very simple processes. Super paramagnetic particles. So now you can vary magnetic properties. So you can see here, these are again magnetic particles, and you can see that they are kind of ferrofluids. If you see the picture, the fluid moves with the magnet. So they are ferrofluid, very stable particles, around 8 to 10 nanometer, again made in room temperature. You can make them in aqueous medium and you can make them in oily medium both. And they have lots of applications in the medical field. These are again silver nanoparticles. Then we worked on graphene and its composites. So that's again some area where we started working on it. And you can see this graphene. And this was basically for microwave absorption applications, very light, ultra lightweight material. And again, we were able to make in quantity. These are two very interesting examples which really did not involve much of synthesis, but more of observation. That is what is very important. We know barium titanate, if we know, it has got very high value of dielectric constant. It is a ferroelectric material. We were working on conducting polymers. Conducting polymers have got two forms, polyaniline. One is base and another is salt. Base is generally a kind of non-conducting and salt is conducting. And base is when non-conducting, its dielectric constant is very low. Now you see the curve here. If you take pure barium titanate, its dielectric constant is 100 plus. But if you add about 5% of polyaniline base, this dielectric constant drastically come down to around 25. Now it is not explained by any law of mixing. When you mix two materials, they should follow the law of mixing. That means they should gradually come down. But it is coming down very rapidly with very small concentration. We were struggling for about 3 months to understand how it is happening, and my PhD student used to come to me daily in the evening. Sir, ye paper, this is the paper. I used to say, nothing is available in this, nothing we are able to get. So we struggled for about 3 months. After 3 months, we could find out and we could explain the results. We also took this microscopic picture. Simple microscope, nothing like electron microscope. Microscopic picture, and what we could see is that this polyaniline base is making a very thin layer around the particles of barium titanate. Now the barium titanate gives you high value of dielectric constant because of interfacial interaction between the particles. Now what we have done, we were able to break this interfacial interaction between the particles, and since we were able to break it, so the basic process which leads to a high value of dielectric constant, that itself was removed. So once it was removed, then you got very low values of dielectric constant. Then if you see the figure here, then for all other lower values, dielectric constant is nearly about same, not varying much, but suddenly it falls down. So this we could explain through X-ray diffraction also. This we could explain through FTIR, because whenever you observe something, this is again for students very important. One study cannot provide you the concrete results. You have to corroborate with at least 1 or 2 more studies that yes, it is really like that. Then only it will be accepted in the journal. Otherwise, it is not going to be accepted. So though we observed the things, but to explain the things, we had to do lots of studies, and we did these studies. This is very interesting. Another example. last example was also, I call it pistol motor research. In the sense that we had two material, we took in a pistol motor and grinded them together and got the results. Here also it is pistol motor research in the sense that we had conducting polymer now, polyaniline, which is conducting. And we had a zinc sulfide material which is semi-conducting but conductivity is very low. Now we know that when you make mixture of the two, what will happen? When you take zinc sulfide, low conductivity. When you take polyaniline, high conductivity. And as you change the ratio, conductivity will move from lower to higher side. But if you see two circles, closely observe these two circles, wherein you are seeing that these two composites have got electrical conductivity higher than that of polyaniline. How it can be? A composite is made, how the conductivity can be higher than highest? This was again very interesting result, and then how to explain? So we worked upon it and we got very interesting results in this. What was interesting? Interesting was that conducting polymers, they give better conductivity when they are crystalline in nature. So crystallinity is higher, conductivity is going to be higher. So that was the hypothesis which was in my mind, and let's try to understand that, and we try to work upon it. And very interesting, of course these were microscopic, very interesting X-ray diffraction studies. The lower curve is that of polyaniline. You get a peak of broad peak of polyaniline. As you increase the concentration of zinc sulfide, you see the polyaniline peak is disappearing. So zinc sulfide is working as a template for polyaniline, and polyaniline is getting better crystallinity. And because of better crystallinity, it is giving you higher conductivity. So you see, you can increase the conductivity of the material if you know real physics behind it. So this is again very interesting result we have got. So these last two examples, when I am saying, these examples were very simple research wherein we had two materials already available with us. We took in a pestle motor, grinded them, did the studies, made the observations, explained the observations, and these two papers have got citations of 100 plus by now, and we had very good comments from the referees because they were not related to the material synthesis, they were related to the interpretation of the results. So it is very important to understand the things, make a right kind of interpretation. That is what is very important. And if we can do like that, we can do wonders. And all these wonders were done under the guidance of my mentor, Dr. N. Kumar. He was earlier director of DRDO. He was my predecessor. And these were my PhD students and also colleagues. It is basically work of them. Thank you. Jai Hind.